So after this, rather clever ideas, we arrived at a good picture. Basically, that's what all undergrads, physics and chemistry students need to know. For a molecule, the energy allowed by quantum mechanics for a whole molecule consists of 3 parts. The first part has to do with what the electrons contribute. Basically, it is the bottom of the binding curve, one number. Then the vibrations of the 2 nuclei will give a vibrational part of the energy. And then the 2 nuclei, thinking about it as 2 balls with a rod, they rotate around. Then it will give a rotational part of the energy. This whole line gives us what the possible energies can be. There are many implications, okay? So this one, I try to help you read this equation. You must follow 1, 2, 3, okay? So let me try it one more time to give you an impression. The first term emphasizes that it is the electrons that bind the atoms. They set the energy scale, the bottom of the curve, and they give the spring constant K from the curvature and set the equilibrium bond length. So you have all this thing here, and then you have a H bar omega here, which is K over mu. But the K is set by the electrons, okay? 4 ... okay? And then comes to this term. For the vibrational motion of the nuclei using this particular angular frequency, that has to do with the steepness of the bond related to the electrons, okay? And it also sets the energy scale for the rotational motion because it is mu R0 squared, moment of inertia, and this preferred thing is set by the electrons, okay? So it is the hidden implication of this formula. Then I would like to give you a picture of this formula, okay? Both are important. So what is the first term? After you solve the electronic part, you get a binding curve. The first term is just a number. So this is 1. Get me? So this is the first term. It's just this value. All right. Now, what is the second term? N plus half H bar omega. What are they? So I'm blowing up, zooming in this curve. So I draw it bigger, and I assume it to be a parabola near the minimum. And inside here, you see this n equals 0 line, n equals 1 line, n equals 2 line, n equals 3 line. These horizontal lines are giving the n plus half H bar omega. That is to say, this is half H bar omega above the minimum, okay? And this is 3/2. This is 5/2 H bar omega. This is 7/2 H bar omega. And there are many more up here. Okay, so now everybody follow? Okay, if you don't like the mathematics, this is the picture you need to carry with you. Right? Now, but that's not the, this is 2. Okay, 2 means this horizontal lines. Okay, the 2 means this term. Okay, but more, we have a number 3. Okay, so look at this thing. and L runs from 0, 1, 2, 3, forever, actually. So how can I draw this? Okay, so here you see there are several families of things. Okay, the first one is drawn for the family under the condition n equals 0. All right, so now for n equals 0, I look at the third term. I would have a L equals 0 for the rotational energy that is 0. So it overlaps with this n equals 0 line. But then I will have a L equals 1, L equals 2, and so on. Now, notice that L times L plus 1 will be slightly farther and farther apart as L goes up. Now, you see the separation increasing. Okay? So this family is the rotational energies attached with the ground state of the vibration. I pause 10 seconds. Do you understand what the last sentence? Now, n 等於0，我就走去個 rotational term. Okay, and then consider L equals 0, 1, 2, 3, 4, 5. And I draw this family. Do you follow? Come on, okay, but it's not the end of the story. I could start with the first excited vibrational state, n equals 1, and again, start drawing L equals 0, 1, 2, 3 for the rotational one. So this family are the rotational energy associated with the first vibrational excited state. Do you understand? 跟唔跟到啊？行嗎？ Understand? Okay. Now, let me tell you one more time what does it mean. It means the following. Given the molecule is in the electronic ground state. So here, don't worry about the upper curve, okay? Those are 20 eV above. You don't do it usually, okay? You need ultraviolet to excite it, okay? But you don't do those experiments regularly in the lab. So basically, always, we will stay on this electronic ground state, but there could be vibrational excitation, n equals 0, n equals 1, and so on. In addition, there could be rotational excitations. That is to say, a molecule could be of this energy. It could be of this energy. It could be of this energy. Okay? These are the energy eigenvalues of the whole molecule. Do you understand? 跟到嗎? Okay. You see, very well, slightly more complicated, but the world will become much more interesting. Okay. Now, this is what I try to explain more a bit later, but I would like to give you some molecular common sense here. The energy scales. You see that I intentionally draw the vibrational one to be the h bar omega to be bigger than the typical difference of rotational states, and it is always true. So a common sense is that the vibrational energy difference, h bar omega, is usually in the ballpark of infrared. You know, visible is something like 1.5 eV to 3 eV. This is what our eyes can see. So you can imagine infrared is something like 1 eV or 0.1 eV. So this is the right ballpark number. And what are rotational things? Rotational things are governed by so this will be a typical energy scale of rotations, rotational motion. Well, you just plug anything like nuclear mass, maybe 10,000 times of an electron. Bond length, well, plug 2 angstrom into it, about right, okay? Just plug in it, then you know. Immediately you see the rotational level, typically the difference are of the order of 0.001 eV. That is to say, if this is 1, that will be 1% of 1, okay? They differ by 1 over 100. So if 0.01 eV, 0.1 eV, this is 0.001 eV. So this is 1%. That is to say, if this is 1, this thing should be much more smaller. But in order to see it, let you see it, this is exaggerated. Okay? Now, have this number with you in mind. This is easy to think, rotational. Last time I mentioned, you put a glass of water into the microwave oven, you are using the rotational motion of the water molecule to generate the heat up. So you immediately know rotational motion of molecules is in resonance of with microwave frequency. And that is the ballpark of microwave photon energy. What is the consequence? We will discuss this in the last part of molecular physics, but I would like to show you so what, okay? So what about this figure? Okay, now believe it or not, if I have a molecule excited going from here, it could go down to there, for example, okay? So there will be a change. Listen to it carefully. There will be a change in both the vibrational state from n equal 1 to n equal 0, as well as the rotational level from a certain L maybe to a L minus 1. Get me? Now, if you account for all possible transitions from an excited down to this family, you will get a very beautiful pattern. So this is a molecular spectrum, usually happen in the infrared range. This spectrum has a name. It is called rotational vibrational spectrum, or even in a short form called rho vibrational spectrum. This is hydrogen bromide, rather beautiful. Okay, and it is a fingerprint of each molecule. Just like the atomic spectrum is a fingerprint of an atom, we have this even, I think, prettier, more beautiful molecular spectrum for each molecule. Later on in our course, we will learn how to read out properties from this beautiful figure. For example, it looks like there is a missing line here, okay? So if we read out where is the missing line, well, what we think is a missing line, that will give us the stiffness of the bond, the spring constant. And more, if you read out this separation, it will give us the bond names. How nice. And that is the experimental way to extract this very important parameters for a molecule. Okay, so we have done a lot of things in an hour. Now, at least I hope most of you have a broad, despite non-mathematical, has a broad understanding of, first of all, why atoms can bind into molecules, and once it binds, how to describe in details of the allowed energies of a molecule, and then what is the consequence? The biggest consequence is this one, molecular spectrum. Okay, so now I gave you the big picture. The next part will be to fill in some of these details. How come this binding curve can come out? Is there a physical way to think about it? The answer is a yes. And then another big guy comes in to help us understand the electronic Schrödinger equation. Okay. I know some of you may be doing condensed matter physics or solid state physics later on. So here is a last remark for this discussion. We discussed von Oppenheimer for diatomic molecule. I think you can easily extend the idea to triatomic or bigger molecules. But I would like to point out, this von Oppenheimer approximation is also at the heart of solid state physics. Solids are atoms sitting in a regular array. So here I just depict it as a square lattice. Of course, they are 3D thing, harder to draw. So the crosses now means, for example, the ions, sodium, so the core without one electron. Then the extra electrons can be wandering around in this piece of solids. How to treat this problem? In principle, the ions are vibrating, they're moving around the equilibrium position, and the electrons are wandering around. So you have this typical full Hamiltonian problem. But in solid state physics, chapter 1, it will say, let's assume the ion to be fixed and solve an electron that is living in this array of ions. What happened to the electronic energy? Now, that is exactly von Oppenheimer approximation. This is a big problem in solid state physics. The chapter is called energy bands, the formation of energy bands. So basically it means solve this. Well, actually, solid problems happens to be easier than molecular problem for the reason you have periodicity, 周期性啊，周期性. Periodicity is easy to see. If you are an electron at this location, you feel a potential energy due to the square lattice. Of course, it is the same as what you feel here, the same as what you feel there. All right, because the solid is very big. The vicinity is the same. So it's like a forest, right? So the trees are planted in a regular way. So you stand here, you look around, you see the same environment as you stand here, you look around, and so on. This is periodicity. Periodicity is a nice thing for you to explore in solid state physics. You do this Schrödinger equation for electrons in solid state, the answer is that you get bands, a range of energy full of allowed states, but there's a range of energy with no allowed states, and so on. These are called band gaps. These are called bands. Okay, even you have the names say conduction band, these are all filled with electrons and so on. Okay, and then these are valence band. Nonetheless, you have this bands. And then afterwards, in chapter 3, chapter 4 of a solid state physics books, you started to learn lattice vibrates. The atoms vibrates, the ions vibrate. Okay, so again, it is the electrons that is given rise to this curve, and the ions are vibrating about this minimum, and then you have many oscillator physics in the vibrational problem that contributes to the famous heat capacity problem of solids. If you have, I wonder in Professor Go's course whether you have arrived at a discussion of the oscillator statistical physics, where you will have the Einstein model. 做咗未啊? Have you done that? You have done that? Really? Good, good, good. Now, wonderful. Okay, now you may wonder. Okay, now you may wonder, what is this springs in the solid? Okay, I hope after today you have a better feeling. It is the electrons. They move around, the wave function provides some potential profile of this form for the atoms to move around. Okay, and you are using Born-Oppenheimer, just what we discussed today in your other course. Of course, the background is not necessary for doing the statistical physics calculation. Okay, are you doing it in counting, guys? Do you count the microstates? Or you are doing it partition function? Or you are doing partition function? Okay, good, good, good. Good. Okay, so we are done with the big picture. So do you have a big picture in mind before we fill in how to do the electronic problem? 对不对? Okay, so now this is the bare minimum. Okay, so there's a question, let me see. How would I know when the interatomic separation from R1 go to 1, the electrons will arrange themselves in a way that resembles? Okay, now let me read the question. It's an excellent question, very deep. I can only answer it very briefly though. The question was, how could I know when the interatomic distance R changes from R1, say, to R2, the electrons can arrange themselves in a way that resembles the eigenstates of a stationary separation at R2, okay? The answer, as you suggest, it is precisely the time scale separation problem or the energy scale separation problem. Okay, that is a very brief answer, Mr. Chen. A deeper answer is there is further theorem in perturbation theory that we can make use of. We haven't discussed it. It is beyond our course because we are focusing on applying quantum mechanics, okay? If you are interested in, there is a part of time-dependent a theory called adiabatic approximation. Okay. By adiabatic approximation, we mean that the time dependence in the perturbation of the Hamiltonian changes very slowly. Okay, attached to it, it is something called adiabatic theorem. Okay, basically it says, now it's very hand waving for my answer. Okay, it says if you are in the ground state of a electronic problem at time t1, the Hamiltonian changes very slowly. So at time 2, that state will evolve to the ground state of the new Hamiltonian at time 2, and so on. Okay, so do you follow me? 跟唔跟到啊？邊個問㗎 ？Mr. Chen。Mr. Chen， 跟唔跟到啊？知唔知我講咩 ？Okay， and we are making use of this adiabatic idea. It follows that particular state. So ground state, you change it very slowly, the Hamiltonian, then you will get to the new Hamiltonian's ground state. You change it slowly, it will follow to the ground state, but of a different Hamiltonian because of time change. You follow me? That? Okay? That? Yeah, okay. So, well, because you asked such a good questions, let me give 30-second more answer, okay? Now, this is beyond the course, okay? I think in 1980 something, someone with the name Michael Barry did a very interesting work for this slowly varying Hamiltonian problem. So he was thinking about a Hamiltonian start at time 0, varying it very slowly, but later time on, it will come back to the same Hamiltonian after a long time. So it's very slowly, okay? But come back to the starting point, okay? So he worked out this adiabatic approximation and how it works. And at the end, he found that there may be a phase after you go around the whole trip that is called the Barry phase. And it becomes a very hot topic nowadays in quantum mechanics, okay? But I will stop any further mentioning of this thing here. Okay. Any further thing? So good. We have done a big part of understanding. Let me see. There is a comment saying, so what you're showing here, the electron does not really have a lot of effect on the whole thing. I would say no. The electrons are responsible for the minimum, the existence of the minimum. Therefore, it is giving rise to bonding. There was a question about what is the significance of the Barry phase. That I think I have to stop the discussion of Barry phase here. I only would like to say it's of significant consequence that many of the, even up to now, many developments of quantum whatever rely on this particular phase. For example, one realized that one can generate something like a magnetic field without buying a magnet, because that phase refers to something like a magnetic field. And when an electron moving around a magnetic field very interesting will happen. Very interesting thing will happen. Okay, so I can only mention that much. Okay, I don't want to divert out too far. Okay, but if you want to learn, I show you the path already. Read adiabatic approximation, see what is the adiabatic theorem, and then go to Berry phase. They are following this sequence. You learn it this sequence, it's very easy to follow. Okay, Mr. Long? Okay, good. I'm happy that you asked questions. So let's start the next part. We have the big picture now. We have step one, solving the electron part. We hope that this can come out. Usually it will. And then this part will feed into the nuclear motion part, giving rise to vibration and rotation. That's the big picture, okay? And we have many fascinating consequences. The most fascinating is the molecular spectrum. For getting molecular spectrum, there was a question posed. You just do infrared spectroscopy. Shine infrared, see what lines are missing, you get a spectrum. Mr. Choi, you asked that, right? Okay, so now I answered that as well. So I clean up all the questions. So now we go back and focusing on how to get some good physical sense in solving the electronic part. It means, can we get good sense of how bonds are formed? In doing so, we would like to introduce the idea of molecular orbitals, or shorthand MOs. It's easy. The solution to the electron Schrödinger equation in atoms give rise to atomic orbitals, 1s, 2s, 2p, those things. But now we have two centers. The solutions to this two centers Schrödinger equation, they are called MOs, molecular orbitals. We would like to introduce a particularly physical picture of the method of linear combination of atomic orbitals in forming molecular orbitals. So in shorthand, it is called LCAO-MO. Okay, it means the following: linear combinations of atomic orbitals using this as the trial wave function for variation calculation. The end results are molecular orbitals, basically it, okay? With this idea, later on, we can extend it to understand a lot of chemistry, including what is hybridization. I think some of you know, maybe have heard of sp, sp2, sp3 hybridization. I hope at the end of this course, you know, you have a better quantum mechanical sense what they are. And then maybe some of you also know delocalizing electrons would lower the energy. For example, what is metallic bond? Why metals can achieve lower energy, right? So this is delocalizing the electron. All these are related to the Schrödinger equation of the electronic part, and LCAO. This simple idea can help us understand material science, solid state physics, and chemistry. So let's start with a difficult problem. H2 molecule. So the electronic problem is this. The Hamiltonian of H2 is 2 electrons, so 2 kinetic energies. Electron number 1 sees A and B. Electron number 2, R2 here, sees A and B. two electron repel, two nuclear repel. So you have this Schrodinger equation. Okay. So if you compare this, it is slightly more difficult than the helium atom problem. Helium has two electrons, but one center. This problem has two centers with two electrons. Okay. So even if you take the center of mass thing, you still unavoidably, you have a two electron problem. Can we do that? Well, roughly, yes. Okay. And then, but we know this Coulomb repulsion term kills the problem. By that, we mentioned it in helium atom that kills the helium problem and make it a real many electron problem that no analytic solution can be found. Then we have to do something like Hartree, Fock, that kind of things to reduce it to single electron problems. Then we use Pauli exclusion principle to fill the two electrons in now into molecular orbitals. Well, so all in all, we can think through the problem in principle, still okay, but complicated. What's next? Simplify the problem, right? We just want to focus on molecular physics, basic idea now. So an easier problem turned out to be not quite a neutral molecule problem, but a molecular ion problem. This is the famous H2 plus problem. What is a H2 plus? I have a H2 molecule, neutral. I take away one electron. So the problem is two center, one electron. So that is the nice thing. I have a single electron, but two centered problem. Okay. So we want to focus on, now this is already a problem. Can you imagine? I have two protons. Hydrogen nucleus is one proton. I only have one electron. The question is already rather fascinating. Can one electron bind two protons? Okay, so the electron must be very busy, right? Hey, don't go away because the two protons repel, okay? But the electrons try to, hey, pull it here, pull it there, hey, stay there, okay? It turns out that H2 plus exists. Experimentalists can make it, it exists. So one electron can bind two protons. And let me give you an even more fascinating story. H3 plus. One electron can even bind three protons. It is found in interstellar dust out there. It's part of astrochemistry. It's not astrophysics. Okay, so this thing, rather fascinating. Okay, so but again, I don't want to go too far. We just focus on H2 plus. We would like to use this simple example to understand what are molecular orbitals, what are bonding state, what are anti-bonding state. Maybe you have heard about it in 1070 chemistry. What is a covalent bond? Okay, this happens to be a covalent bond. So what is the quantum mechanical problem? The quantum mechanics problem is one electron. Easy. Quotation mark, two center. Okay. Now, the origin is the center of in the middle between two proton A, proton B. The nice thing is that they are the same proton. They are the same. They are different protons, but they are the same particle. Okay. So I have two center, one electron, coordinate R. Okay. The separation is R minus RA, so called RA and RB respectively. So write down the Hamiltonian, one kinetic energy term, happy, right? Single electron. The electron sees proton A, see protons B, they are attractive. Then we are done. But it is a molecular problem, therefore we must account for two proton repel. Okay, but now we are Born-Oppenheimer approximation. You give me an R, this is a number. Okay, so it's a constant. So get a feeling of what the electrons feels in this problem. Okay, so the electron is under the influence of a Coulombic attraction due to center A and center B. So if I write this 2 as a single electron potential energy function felt by the electron, it is what it sees, two terms combined. We want to solve this electronic Schrödinger equation. Okay, we want to see in particular, try different R, what is this profile? Okay. So here I repeat this Schrödinger equation here, okay? If we've only focused on this potential energy profile, we may as well put this term to the right-hand side. You minus this term over, okay? And then you can focus on solving this Schrödinger equation first. If you know this, now this is different from this one, okay? This has the term left out. You first solve this one. After you solve this one, you add back a constant. It is this thing. Okay. So we will focus on what this solution looks like. Therefore, the first thing is to get a sense of what this two-centered Coulomb attraction is about. So let's look at what one term looks like. The electron sees proton centered at A. So this will be the center of the proton number 1. Okay. So minus 1 over R. Now it is 4-dimensional plot. I cannot plot it out. So I use a 2-dimensional analogy. Minus 1 over R is something like this. This is the center. Away from it is R. Okay. So it is like a farmer's hat, inverted. So it's something like that. But now I have 2 of them. If they are very far apart, it's something like this, far apart. Now you can imagine, I would need to try different separation, right? Shorter and shorter. So it is minus 0.5, add to minus 0.5, it is minus 1. So it's even lower, all right? So if they are far apart, this is a, you can imagine that this is a cut along R, all right? So very far apart, it's like this. If it is closer, in the middle, it started to see minus F to a minus is lower. If even closer, it is even lower. Okay, now do you sense what the electron feels in the Schrödinger problem? Okay, so if not, then I would like to pose the following problems to you before we end today's class. Now, first of all, the method to solve this thing, we will be using LCAO, linear combination of atomic orbitals. For the reason, molecules are formed by atoms. We don't want to waste our knowledge of atomic orbitals. We would like to say the solution to this may be obtained by combining 1s, 2s, 2p from atom 1, the left-hand side, and 1s, 2s, 2p from atom 2, the right-hand side. Let's write a linear combination of it and let that be the trial wave function for this molecular problem. Do you understand? 明唔明啊？你諗唔諗到啊？ Okay. Once you have this, in your mind, do you see a big matrix problem? And then you diagonalize it, you get the molecule's energy. Get that? Okay. But I would like to throw you the following problems before you go. An atom in a simple picture is like a 1D finite well, right? Because there are discrete states here that works like 1s, 2s, and so on. Okay, so this is a model of an atom playground. What is a molecule then? This looks quite like a molecule, right? In the middle is lower, so this thing is a molecule. And let me tell you, in many chemistry books, this is the first problem in the molecular chapter. Solve this. Even if you don't know any background, you can solve it, right? You may try this way. Write down the wave function in region 1, region 2, region 3, region 4, region 5. Apply boundary condition, connected it at the boundaries, and then you find what are the allowed energies. Good. Those are the molecular MOs, allowed energies. Okay. If you have different atoms, solve this. Okay. But for this problem, we would like to solve it in a different way. The way is, I take the left atom, I solve the single well problem. I know the ground state, I know the excited state. The right atom, I know this states. I would like to combine them to form the solution to this problem. This is LCAO MO. Okay, so I would stop here today. If you really want to play with your quantum mechanics, try this in two different ways. Write down the wave function in every region, connect them, or see whether this will also help you solve the problem. Okay, both ways works in principle. Okay, so I will stop here today, and then we will continue on with this LCAO idea, and you will see, wow, very simple thing. We can understand a lot of chemical bonds. So we are done today. I will stay around to answer your questions.